Okay. Uh, the title of my paper is Set the reference number of forest versus brooms. Firstly, let's review the definition of set reference number. If G and H are two graphs, we write F arrows GH to denote that. G or H is a monochromatic subgraph of G in every two column of edges um, of F. The set reference number height R GH denoted by this. This is the set reference number. Okay, let's see the basic proof method. For the upper bound, we construct a graph edge such that F satisfies this F arrows GH. Then the number of edges of F can be the upper bound of the set reference number. For the lower bound, it's any graph with a given number of edges can find a red-blue edge column such that these graphs contain neither a red copy of G nor a blue copy of H. Okay, let's see the brooms. Bmn is defined as this. Here are n vertices and here are m vertices. So the number of vertices of Bmn is m plus n plus 1, and the number of edges of Bmn is m plus n, and the maximum degree of Bmn, delta Bmn, is equal to n plus 1. Here is a B3n, and here is a B4n. Okay, let's see the mean result. The results of the paper are shown in the table. Okay, let's see the results of matchings versus brooms. You avoid to red matching, so the subgraph induced by the red edge in F is a star. Let's say the upper bound of 2p2 Bmn. We construct a graph look like this. Here is a cycle. Here the cycle. The cycle is C2m, and here is m vertices, and here m vertices. Here is a star, center of a star. Here are n minus 1 vertices, and here are n minus 1 vertices. So we can check that this graph for any two column, we can either find a red 2p2 or a blue Bmn, so it can as the upper bound of this. Next we say the 2p2 B3n. The result of this is 2n plus 5. The upper bound is shown as this. Let's say the lower bound. For the lower bound, the maximum degree of f is very useful. If the delta f less than or equal to n, then f is not contain a B3 as a subgraph. Also, the maximum degree of f should be not too large. Otherwise, we can color a red star so that the red edge as many as possible. So we only consider the cases of the delta f equal to n plus 1. Let S be the number of vertices of degree n plus 1. We have a claim that S not more than 2. The proof is very simple. Here n is greater than or equal to 5 is make sure that the large degree vertices not too much. Okay, S equal to 2, that we have two vertices such that the degree equal to delta f equal to n plus 1. So if UV in EF, we can color UV red. Then then the delta f minus uv less than or equal to n. So there's a no blue copy of B3. So in the case of UV not in EF, and the intersection of the neighborhood of U and the neighborhood of V is not an empty set, so we can choose a W from this, and we can color a right path. Next, we suppose UV is not in EF, and the neighborhood intersection is an empty set. So we consider F minus U and F minus V, and next, if F minus U is not isomorphic to B3n, then the coloring we find is desired coloring is similarly to this case. So we have F minus V isomorphic to B3n, and F minus U isomorphic to B3n, F minus V isomorphic to B3n. So we can have two edges, E1, E2, that E1, E2 in F minus U minus 1. So we can color E1, E2 red. The proof method of 2P2B4N is the same as the proof method of 2P2B3N, so it is skipped here. Okay, let's say the result of P3 versus brooms. Similar to matchings versus broom, in order to avoid red matching, here is in void to have a red P3. The subgraph induced by red edge in F is a matching. Let's say this result P3 B3n. This is the upper bound. The proof method is the same, so we firstly determine the number of the vertices of degree greater than or equal to n plus 1 is only 1. There are only 1 vertices. Okay, next we see the delta f. If the delta f less than or equal to n, we have this. If the delta f equal to n plus 1, we have this. Also, the delta f should be not too large. So we only need to consider the case of delta f equal to n plus 2. And next, we consider the graph f minus v. The degree v is equal to n plus 2. Okay. Next, the f minus v. If the f minus v is not isomorphic to K3 and not isomorphic to K13, then we can find the 2P2 in f minus v and color it red. So the f minus v isomorphic to K3 or f minus v isomorphic to K13. Okay, next we consider the NV intersect V f minus v. Let's say here are two cases. In this case, here there's a subcase 1.2 or 1.1 and 1.2. Let's say two graph. This graph is 1.1. We find Vi here, and and color this as red here. If here is a subcase 1.2, we notice that the vertex of this graph let's say this is equal to n plus 3 less than the number of vertices of B3n. So F not contain B3n. Okay, here is the subcase 2. It's very simple. Okay, next say P3 B4n. The proof method is very the proof method is similar to the P3 B3n. The upper bound is is here. We construct the graph. So the lower bound, firstly we determine s equal to 1, and we consider the delta f, and then we only consider the delta f equal to n plus 2, and we only consider this graph f minus v. The f minus v must satisfy such condition. The maximum matching is 2, and contain a P4 as a subgraph, and delete any matching of H. Here always P4 in H. So this graph only be this 5 edges. So so in this case, we color this edge red, and in this case, we notice that the vertex is less than V before. Thank you.